So let's now look into the physical properties of stereoisomer, that is optical activity. The physical and chemical properties of the two enantiomers, as we explained earlier, are identical except their interaction with your chiral compound. So only difference is what happens when they react with the chiral compound to form a diastereomer. So that is the only difference. Rest all their physical properties and chemical properties are identical of the two enantiomers. They have identical physical except how they rotate the plane polarized light. Very important. So all the melting point, boiling point, everything is same, but only thing they differ is the how they interact with the plane polarized light. The plane polarized light is a light that oscillates in a single plane. So when all the rays of your lights oscillate in a single plane, they are parallel to each other in a single plane. Such type of light are called as your plane polarized light. It is known as plane polarized light or polarized light. The plane polarized light arises from by passing the ordinary light through a nickel prism, that is your polarizer. So when you pass your ordinary light through a plane nickel prism or a polarizer, whichever is going in all the direction, it will be made to oscillate in a single plane, that is parallel to it. So these are known as polarizer. And a polarimeter is an instrument that is used that allows the plane polarized light to travel through a sample tube containing an organic, and it permits the measurement of the degree to which the organic compound rotates the plane. So with the help of a polarimeter, you can measure how much the compound rotates the plane polarized light. Okay. So with chiral compounds, the plane of through an angle of, as we said, it rotates through an angle of alpha. Okay, and the angle alpha is the measure in degrees, and it is called as observed rotation. So whatever observation we get when you read through the plane polarized light, that gets deviated, that is known as observed rotation. And the compound that rotates the plane polarized light is said to be optically active. So the criteria for compound to be optically active means it should rotate the plane polarized light. Okay. Now see, this is a diagram of your polarimeter. So there is a source, ordinary light, which directs in all direction. It passes through a polarizer, that is a nickel prism or something. So when the moment it passes through that, they oscillate in a single plane. Because it gets converted into a plane polarized light. Now this light passes through your sample tube, which contains a chiral compound, and these chiral compounds rotate the plane polarized light, and that rotation is measured by the analyzer. So you rotate the analyzer and you measure the degree of your deviation. Okay, you measure the degree of deviation of your plane polarized light. This is how you try to measure the degree of deviation, that is rotation. So now let us see what is the rotation of plane polarized light. Can be in a clockwise or anti-clockwise direction. So it can rotate in clockwise, that is to a right side, or it can rotate to the left hand side. Both the ways, according to the enantiomers, it can rotate the plane polarized light. Now if the rotation of light, plane polarized light, is in clockwise direction, if the rotation of the plane polarized light by the compound is in clockwise direction, then the compound is said to be dextro-rotatory. So if it rotates towards in clockwise or towards right, then the compound is said to be dextro-rotatory, and it is labeled as D, small d. Dextro-rotatory is labeled, it is denominated by small d or cap plus sign in bracket. In bracket plus sign. Now the second part. So some of the compounds may rotate in anti-clockwise direction. So the rotation, if the rotation is in counterclockwise or anti-clockwise or towards the left hand side, the compound is said to be levorotatory. The compound is said to be levorotary, and the rotation is labeled by small l or a negative sign. So negative sign or a small l represents your levorotary compounds. Do not get confused between the capital L and the capital D in case of DL relative configuration. Remember this thing, very important. It represents small d and small l represents the rotation of your plane polarized side. If it is towards the right or clockwise direction, it is known as dextro, small d or plus. If it rotates in counterclockwise direction, it is known as minus, or L, small l, that is known as levorotary. Okay, the enantiomers that rotate the plane of flow in equal extent but in opposite direction. So you know that if one enantiomer rotates in right hand side, the other enantiomer of it will rotate in the left hand. So if one is D, the other enantiomers will be L rotatory. Okay, next levorotatory. Thus, if an enantiomer it rotates the plane polarized light to plus 5 degree, then the same concentration of the enantiomer B rotates at minus 5. So both the enantiomers A and B, which are mirror images of each other, rotate. If they are in equal concentration, they will rotate in exactly opposite direction, equal amount, but in exactly opposite direction. So this is how you try to differentiate between the two enantiomers. There is no relation between R and S with prefix plus and minus. So your absolute configuration has no relation with your rotation. Your R can be positive or negative. It can rotate the plane of polarized light in the left or right. So there is no relations between your prefix R, capital R and S, that is absolute configuration, with the rotation of your plane polarized light. Okay, there is no relation between your optical relation and your configuration. Keep this thing in mind, very much important. Now, what is specific rotation? Now, that is observed. Alpha is your observed rotation. Now, the definition of specific, it is the number of degree of rotation. It is degree, that is alpha. If 1 decimeter, that is 10 centimeter long tube is used and the compound being examined is present at the concentration of 1 gram per ml. So it is the degree of rotation observed. So it is the degree of rotation observed when a sample tube of 10 centimeter or 1 decimeter long tube is used and the compound that is examined is in the concentration of 1 gram per ml. So such type of rotation, the observed rotation in such a condition is known as specific rotation. It is known as specific rotation. So what is specific rotation? It is the number of degree of rotation observed. If 1 decimeter, that is 10 centimeter long tube is used and the compound being examined is present at a concentration of 1 gram per ml. Very important. This is usually calculated from the observations with the tubes of other lengths and different by means of this equation. So specific, if you want to keep it in different concentration, we can also do it, but we have to put it into this particular. So what is specific rotation? That is denoted by alpha in square bracket. What is alpha? Degree of rotation. And what? And if it is written in square bracket, okay, close bracket, then it is known as specific rotation. And it is given by the formula alpha divided by L into C, where alpha is the observed rotation, L is the length of the sample tube in decimeter, and C is the concentration in grams. So what concentration you are using, what length of the tube you are using, and you check the observed rotation, you can put it in this equation to get your specific rotation of your chiral compound. Okay. Now, what does this specific rotation depends upon? It depends upon the nature of the substance, concentration of the nature means whether it is dextro or levorotatory, concentration, length of the polarimeter tube, and the wavelength of the incident monochrome. Usually 598 nanomolar wavelength is used for your observation, and the temperature, because temperature plays a very important role. Temperature can change the conformation. So these are the 5 criteria on which the specific rotation depends. So the 5 criteria are nature of the substance, concentration of the solution in gram per ml, length of the polarimeter tube, wavelength of the incident monochromatic light, and the temperature of your sample. Okay, these are the conditions which are necessary to observe the specific rotation, to calculate the specific rotation. Now, some other physical of our optical purity. Now, let's see what is enantiomeric axis. What is enantiomeric? It is used to measure the optical purity of the compound. It is measured. It is used as a measure how much one enantiomer is present in excess of the other in an enantiomeric mixture. So there will be in a racemic mixture, there will be both the enantiomers, A and B. So how much is the concentration of one enantiomer in that racemic mixture in comparison to the other can be found out by the term called enantiomeric axis, and it is denoted by EE. Enantiomeric is denoted by EE, and it is given by one of the formula, percentage of one enantiomer minus the percentage of another enantiomer. You know the percentage of one enantiomer, you know the percentage of another enantiomer, you can find the enantiomeric axis. That is the purity of your optical purity of your sample. Now let us consider an example. So from the example, it was found that the mixture contains, the racemic mixture contains, racemic mixture means both the enantiomers are present. So the mixture contains 75% of one enantiomer and 25% of another enantiomer. So what is the enantiomeric excess in this case? 75 minus 25, that is 50%. So that is your enantiomer. Thus there is 50% excess of one enantiomer over other in an reaction mix. Means one enantiomer is present 50% more than another. This is how you try to find out the enantiomeric excess. There is one more method where you can calculate it. There is one more method where you can calculate the enantiomeric axis. This is how can you calculate. You have to know the specific rotation of the mixture. First thing what you have to know the specific rotation of the mixture, and if you know the specific rotation of your pure enantiomer, then you put the enantiomeric axis can be calculated by the formula enantiomeric axis is equal to specific rotation of the mixture divided by the specific rotation of the pure compound, pure enantiomer into 100. So you got the specific rotation of the mixture, you got the specific rotation of your pure compound. If you know, then you can find the enantiomeric axis of your specific rotation of your compound will be specific. You can find it out. It is standard. And if you by calculating the specific rotation of the mixture, you put it in this particular formula, you will come to know the enantiomeric axis. In short, you will come to know how pure your compound enantiomers are there in your mixture. So let us take one example. So optical purity or enantiomeric axis can be observed rotation, specific observed specific rotation divided by specific rotation of pure. That is the, and if you multiply it by 100, it will give your optical purity. So sample of 2-bromo observed was 9.20 and the pure sample it was 23. So you take, that is 0.4. 0.4 into 100, that is 40%. So your, this means that one of the enantiomer is present 40% more than the other. Okay, so the other mixture concentration will be 60%. So total number of amount of enantiomeric in the mixture will be 40 plus 60 divided by 2. That is your 70%. Okay, this will be the concentration. This will be the concentration. So one enantiomer will be present in 70% and other enantiomer will be present in 30%. This is how you can calculate the enantiomeric purity or enantiomeric axis. Okay. Now the physical now continuation of physical properties of stereomer, the racemic mixture. So what are racemic mixture? Equal amount of two enantiomer is called racemic mixture. Okay, it is known as racemic mixture. If there are unequal, they are known as racemic mixture, and racemic mixtures are optically inactive. The racemic mixtures are optically inactive because two enantiomer rotate the plane of polarized light in equal direction but in opposite direction. So they cancel each other. So there is no, so if you mix two enantiomers together, you get a racemic mixture and the observed rotation will be zero if it is in equal ratio. Now let us see the properties. Enantiomer A melting point is same as that of your B. Boiling point is same, but in comparison with this, equal in magnitude but in opposite. B also same, only thing opposite. But in the case of racemic may be different from A and B, and the observed rotation will be, melting point may be different, but observed rotations will be zero. Okay, just give me. Okay, this is the properties of a racemic mixture. Now what is the next topic is racemic modification and resolution of racemic modification. What is racemic modification? Racemic mixture is a mixture of two equal amounts of both the enantiomers. Hence they are optically active. Racemic modification is nothing but equimolar mixture of a pair of enantiomers. These definitions are very important. Okay, racemic mixture or racemic modification is nothing but equimolar mixture of a pair of enantiomers. Okay, it contains both the enantiomers in equal concentration. They are known as racemic modification. And racemization is nothing but a process of converting an optically active into racemic modification. That is conversion of an optically active into its two enantiomers in equal concentration. That is known as racemization. So what is racemic mixture or what is racemic mixture or racemic modification? It is nothing but equimolar mixture of both the pairs of enantiomers. And racemization is a process of converting an optically active compound into its racemic modification or a racemic mixture. So these definitions are very much important. Okay. Now, different methods for racemic modification. Different methods for racemic modification. How to convert an optically compound into an racemic mixture. What is the mixing? The best method is to mix equal proportions, equimolar proportion of both the physical mixing. Next is synthesis of chiral compound from a chiral compound. You cut and so let's take an example of prochloride. If you got an carbonyl compound, okay, got a carbonyl compound, you react it with an to form an alcohol. So when you convert an carbonyl which does not contain a stereogenic center, when it gets converted into an alcohol, you get a stereogenic center. So there may be two possible configuration. There may be two possible configuration that can be attained. So this is how you prepare a racemic mixture from a chiral sample, because your carbonyl group will not be because it is sp2 hybridized carbon. So it will not be a stereogenic center. But when you convert into an sp3 hybridized carbon, that is your alcohol, primary alcohol or a secondary or tertiary alcohol, it becomes a sp3 hybridized carbon. So thus you can convert an achiral compound into a chiral. Racemization under the influence of light, heat and chemical reagents. So you can use different chemical reagents to convert your optically active compound into an optically inactive, that is your racemic. So these are the three methods for preparation of your racemic modification. The next topic is chiral resolution. Please mention, it's the most important topic, chiral resolution. Now what is chiral resolution? What is chiral resolution? In stereochemistry, it's a process for separation of racemic compounds into its pure. Racemic modification is conversion of an optically active compound into its racemic mixture, but chiral resolution is exactly opposite. What it is? It is a process of separation of racemic compounds, that is racemic modification, into its pure enantiomer. So from the racemic mixture, you try to separate out each of the enantiomer. This process is known as chiral resolution. This process is known as chiral resolution and is the most important tool in production of optically active compound. Optically active and pure drugs or compounds. So chiral resolution is a chemistry, is a process in stereochem. It's a process for separation of racemic compounds into its pure enantiomers. okay, into its pure enantiomers. Now let's see the methods for resolution of a racemic modification or a racemic mixture. First is your mechanical separation, second is your seeding method, third is your biochemical method, fourth is your chemical method, fifth is your kinetic method, and sixth is your chromatographic method. Now let's go one by one. What's the first thing? Mechanical separation. So what is this mechanical? Use tweezers and all. Initially they used to see the different isomers because they'll have different structures. So according to that crystal structures, they will try to separate it. Difference in the crystal structure will be observed and they are handpicked using your microscope. They'll be handpicked using magnifying lenses or microscope. So example is crystals of ammonium, racemic ammonium citrate. Okay, so can be separated using this method. Next is your seeding method. What is this seeding method? We have studied in recrystallization process. So what do? You put a pure compound inside that. You put a pure compound in a mixture. So what it will do? It will separate out the pure, the form which is with which it is associated. Okay. So what happens? So first you have to prepare a supersaturated solution of a racemic mixture. Yes, it's the first part in your recrystallization. Then add crystal of one enantiomer, pure enantiomer, as a seed. So that will initiate your seeding. So it will group your similar enantiomer across it, and that will help to recrystallize out that particular enantiomer. So that particular enantiomer will come out from the racemic mixture and it will be in a pure form. So this is known as seeding method, where you put one pure enantiomer into that compound, into that mixture, supersaturated mixture, that will recrystallize your one enantiomer from the racemic mixture. That is the seeding method. That is your seeding method. Now let's go for the third. So first one is mechanical, using tweezers. You check because of the change in your crystal structures. You can see it on the microscope and you can separate it. That's mechanical. One is seeding. You put your pure enantiomer into a supersaturated racemic mixture. So your one of the enantiomers separates out. That's one of the method. Now third is biochemical. So what do you mean by biochemical? Biochemical means you use microorganisms. It's a process where one of the enantiomer is destroyed. In biochemical process, one of the enantiomer is completely destroyed. Why? Because micro absorbs one of the enantiomers. So it will take away one of the electrons, enantiomers, and leaving out other enantiomers, like plus or minus. In case of, let us take an example of penicillin glaucum is added to ammonium tartrate. It is added to a racemic mixture of ammonium tartrate. What does this penicillin glaucum do? It will decompose the D form, dextro form of this thing. Your dextro form of your ammonium tartrate is completely used up by your penicillin glaucum, and left is what? Only your levo form. Your levo form is unaffected, and this can be separated out from the mixture. This can be removed. So the main drawback of this thing is that half of the material gets destroyed, it gets consumed by the micro, and half is retained. So you should know the specific one. If you know which one you have to isolate, then you can use this biochemical method. It's a slow process and only small amount can be separated. So this is the drawback. So in case of biochemical method, it's a destructive method where one of your enantiomer is completely used up. It gets completely used up, and you use microorganisms for your separation. Example, penicillin glaucum used for separation of your ammonium tartrate from racemic mixture, where D isomer is completely used and L is left. L is left. Your L isomer is left. Okay, unaffected. This is how you can separate. Now the fourth is what? Chemical method. Now fourth is what? Chemical. This is the best and practically used method. This is the best and practically used method. So what do you do in this thing? The racemic mixture is converted into a diastereomer by reacting with an optically active compound. Okay, separate the diastereomers. thus you obtain a pure chemical. This is through various chemicals. So what is the, and we have studied enantiomers have got same physical and chemical properties, but diastereomers have different physical and chemical properties. This can be used for the separation. They can be used by fractional distillation, fractional crystallization, or crystallization process. The diastereomers can be easily separated. So what you do, you convert your enantiomers racemic mixture into an diastereomer by reacting with an optically active reagent. Then you separate the diastereomer that is formed because of the difference in their physical and physical properties. Use any distillation crystallization method to separate the two in a diastereomers, and then again reobtain your enantiomers by using various chemical reactions. Now let's go for an example. Okay, let us take a racemic mixture of an acid. You take an racemic mixture of an acid, you treat it with an pure enantiomer, that is amine. So when you treat it with an amine, you get a diastereomeric salt. You get a amines reacts with your acid to form an amide. You get both the things. Now these reactions and this salt that is formed, they are not enantiomer, but they are diastereomer, and diastereomers can be separated. Various techniques like recrystallization. And once these diastereomers are separated, you get two different diastereomers separated. Then you do treat it with your strong base. When you do treat it with the strong base, the amide bond which is formed hydrolyzes, and you get your pure enantiomer. You get your pure enantiomers can be separated. So this is how you can use a chemical method for separation, and this is what is used in industry for separation of your racemic mixture. Used for the separation of your racemic mixture. Now the kinetic method. So what is kinetics? Kinetics means rate of reaction. Kinetic means rate of reactions. So in the reaction, the chiral reaction partners or a catalyst enantiomer specific displaces different. So there are catalysts which are present, there are various chiral reagents which are present. The enantiomers will react with it in a different rate. So this can be used for the separation. How they react in presence of that catalyst. One enantiomer will react fast, other will react slow. The product which is formed can be separated, and thus you can separate your enantiomer depending upon the rates of the reaction. But the only criteria which is necessary is that there should be a large enough difference in the rate of reaction. Then only it is possible. Then only it is possible. So if you can see, starting material 1, R and S, chiral reagent, the product and your starting material can be separated. Okay, this is how you do the separation using kinetic method. And the last one is chromatographic method. The last one is that is selective absorption method. That is known as, it is using a column, HPLC gas and all can be used, where it has got an active absorbent in the column. So your reagents get attracted, one enantiomer gets attracted and other gets. So this is how you use. Absorbents like starch, sugar, quartz, etc. are used. Techniques are gas chromatography, HPLC, thin layer chromatography and column chromatography used for the separation of your racemic mixture. Okay. Now elements of symmetry. See, what are these elements of symmetry? So as you have said, compounds, though it contains stereogenic centers, are said to be achiral. Why they become achiral? This is one of the reasons. Elements of symmetry. If any one of these elements of symmetry is present in your molecule, in a compound, chiral compound, then the compound becomes achiral. Now let's see what is elementary. Molecules that are achiral or stereogenic in nature form non-superimposed mirror images and are asymmetrical as a whole image, and they would deflect the plane of light. So a normal chiral or a stereogenic molecule will have all these criteria. It will form a non-superimposed, it will be asymmetric, and it will rotate the plane of plane polarization. But molecules forming superimposable mirror images means they overlap each other on their mirror images, are symmetrical in nature. Why? because they are symmetrical in nature and do not deflect the plane polarized light. These molecules are said to be optically inactive. These molecules are said to be optically inactive. This symmetrical molecule possesses any one of this element of symmetry. So there might be any one of this element of symmetry within this molecule, so that they are superimposable on their mirror images and they do not rotate the plane of polarity. Now let's go one by one. First is plane of symmetry. What is plane of symmetry? Plane of symmetry is defined as that element of symmetry in which the molecule is divided into two equal halves. In which the molecule is divided into two equal halves. One half is the mirror image of the another half. So if you can slice the molecule such that your upper part of the molecule is exactly the mirror image of your lower half. Due to this presence of mirror images forms within the molecule, the total deflection of plane polarized light is zero. So when there are mirror images of each other within the molecule, then the total rotation of plane polarized light is zero. This molecule exhibits optical inactivity. These molecules exhibit optical inactivity, and this optical inactivity exhibited due to an inherent property of the molecule, because this property is within the molecule. This is an inherent property of the molecule. Thus the molecule is said to show optical inactivity due to internal compensation, because of the internal they have plane of symmetry within the molecule. Examples: mesoform of tartaric acid. So if you see tartaric acid over here, COH, your first carbon contains COH, OH and H. On the OH on the right, H on the left. You look out for the second stereogenic. It also contains COH, OH and H. OH is on right, H is on the left. So if you try to draw a line in between the two, this compound contains an internal. This contains an inherent internal property, that is, they are mirror images of each other. They contain a plane of symmetry between the two chiral atoms. That's why they are said to be a chiral. So this particular symmetry is known as element of symmetry is known as plane of. It is an internal compensation. It is internal because of the internal plane of symmetry. They are mirror images. Now let's go for the next, center of symmetry. What do you mean by center of symmetry? The center of symmetry is the element of symmetry in which a line, just see in the structure, when you draw a line from any group of a molecule passing through the center of the molecule, you take a line, draw from the center of molecule and meets an identical group extended to be at an equidistance from the center point. So you draw a line from diagonally from one point to another, and if you have got the same group which are equidistant from the center point, okay, which are equidistant. Example, you take the particular example 1,4-dimethyl cyclohexane. You got a methyl group at the first position and a methyl group at the fourth position, and they are, when you draw a line, they are equidistant from the center. Imaginary line, when you draw from the center, these two substituents are equidistant from the center and they are connect to each other diagonally. So such type of symmetry, if their molecules show, then they are said to have a center of symmetry and the molecule is said to be a chiral, and the two substituents are equidistant from the center point. Okay, this is an example of 1,4-dimethyl cyclohexane center. Now second example is your 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid. This is the entire molecule. You see at this compound, you draw COH and COH. You draw a diagonal line coming from the center. The COH meet each other. From methyl and methyl, when you draw a center joining each other, they meet each other. Okay, when you draw diagonally, and they are equidistant from the center because it is a square. Cyclobutane is a square. It is square. So they are equidistant from the center. So such type of molecule try to possess center of symmetry, and the molecule is said to be optically inactive because of center of symmetry. Now let's come to the next, axis of symmetry. Next is axis of symmetry. What do you mean by axis? You got a central axis is nothing but a central line which is equidistant from the four corners of your molecule, central border. Okay, a molecule which possesses an axis of symmetry, if rotating a molecule by a certain angle around the axis. So you got an XY axis, you got this particular molecule, that is 1, 2, 3, 4 tetramethyl cyclobutane. Okay, when you try to rotate the molecule around the axis, okay, you as is passing through results in an arrangement similar to the arrangement before the rotation. So when you try to rotate this molecule, if you see, however you try to rotation by any angle, like 90 degrees, you get the same orientation. You get the same orientation. You can see the structure 3 and 4. If you try to rotate it, you get the same orientation. The rotation of the molecule by an angle of 90 across the axis passes through the center of the molecule perpendicular, results in the same structure. Okay, so such type of compound are said to possess axis of symmetry, and if such compounds possess axis of symmetry, then the molecule is said to be a chiral. The molecule is said to be